In this lecture, we solve some problems of transmission lines based on the theory which you have developed so far. We will solve some problems analytically, and later on we will go to the solution of the problems by graphical means, that is by using the Smith chart. Let us consider this problem here. A lossless transmission line has 75 ohms characteristic impedance. The line is terminated in a load impedance of 50 minus j 100 ohms. The maximum voltage measured on the line is 100 volts. We have to find the maximum and minimum current and the minimum voltage on the line. Also, we have to find out at what distance from the load the voltage and current are maximum. This problem can be solved either analytically or graphically. We will solve here this problem analytically. So, what we are given here is that characteristic impedance, which is Z0, that is given as 75 ohms. The load impedance, which is ZL, is given as 50 minus j 100 ohms, and magnitude of the voltage maximum on the line V max is given as 100 volts. So, mod V maximum is given as 100 volts. Using this information, then we have to find out the other parameters like voltage and current minimum and the distance of the voltage minimum from the load point. First step in all this calculation is the calculation of the reflection coefficient. So, now I know the load impedance, I know the characteristic impedance. So, from here I can write down the reflection coefficient at the load point gamma L, which is ZL minus Z0 divided by ZL plus Z0. If I simplify this complex expression, I will get the gamma L that will be equal to 0.64 with an angle of minus 65.3 degrees. So, the magnitude of reflection coefficient mod gamma L, that is equal to 0.64, and the angle of the reflection coefficient phi L, that is equal to minus 65.3 degrees. The next step would be that once you know the magnitude of the reflection coefficient, since nothing is told about the line, we take liberty to choose the line to be lossless, and therefore, the magnitude of reflection coefficient remains same on every point on the line. So, we know that the maximum voltage which you see on the line mod V maximum, that is equal to mod V plus into 1 plus mod gamma L. We are given this V max voltage, which is 100 volts. We know now the modulus of reflection coefficient. So, we can find out the magnitude of the incident wave, which is V plus modulus. So, from here we can substitute that this 100 is equal to mod V plus into 1 plus 0.64. Inverting this relation, we get mod V plus, that is equal to 100 divided by 0.64, that is equal to 60.8 volts. Since we know the magnitude of reflection coefficient, we could calculate V max. We can calculate I max also, because once you know the V plus quantity, we can calculate I max. However, we know from our analysis that the maximum current seen on the transmission line is nothing but the maximum voltage divided by the characteristic impedance. So, we know V max, so we can divide this quantity by the characteristic impedance Z0, and we can find out directly the quantity which is the maximum current I max. So, from here I can get the maximum current seen on the line I max, that is mod V max divided by Z naught, that is equal to 100 volts divided by the characteristic impedance, which is 75. So, that gives you the maximum current, that is equal to 1.33 amperes. The I minimum which we get on the line, mod I min, that if we go back to the expressions of the minimum and maximum currents, that will be mod V plus divided by Z naught into 1 minus mod gamma L. We know this quantity V plus, which is 60.8, Z0 is 75 ohms. So, this is 60.8 divided by 75, 1 minus 0.64, which is the modulus of the reflection coefficient. So, from here I can get the value of I min, that is equal to 0.29 amperes. So, the maximum current which you see on this line is 1.33 amperes, and the minimum current which you will see on this line is 0.29 amperes. Once you know the minimum current on the line, we can find out what is the minimum voltage, and that is mod V min, that is nothing but Z0 into mod I min. So, that is equal to 75 into 0.29. So, that is equal to 21.88 volts. So, this line has a maximum voltage of 100 volts, minimum voltage of 21.88 volts, maximum current of 1.33 amperes, and minimum current of 0.29 amperes. Now, we are also have to find out what is the location of the voltage and current maximum on the line. For this, we have to go to the basic relation of the two travelling waves, and when the two travelling waves have a constructive interference, that time we have a voltage maximum. When the two waves have a destructive interference, we have the voltage minimum, and at the same location we have the current maximum. So, we know that the phase difference between the two waves, the forward and the backward wave, that is given as the load reflection coefficient phase minus 2 beta L. So, when this quantity phi L minus 2 beta L, if it is even multiples of pi, that time the two waves will have a constructive interference and I will have a voltage maximum. When this is odd multiples of pi, that time we have destructive interference and we have a voltage minimum. So, in general, when this quantity is equal to plus minus 2 m pi, where m is an integer quantity, we will get the voltage maximum. So, the condition for voltage maximum is when the phase of the reflection coefficient at the load minus 2 beta L is equal to plus minus 2 m pi, that time the two waves have constructive interference and we get a voltage maximum. So, from here we can get 2 beta L, that is equal to phi L plus 2 m pi. I have chosen here the sign positive because I want to get the lengths which are positive. We are measuring all the lengths now towards the generator. L equal to 0 is at the load point. So, all the lengths which you are going to measure from the load point are the positive lengths. So, I have chosen the sign in such a way that I get all the distances which are positive. Substituting now for beta, that is 2 pi by lambda, and substituting for the phase of the reflection coefficient which we have calculated here, which is minus 65.3 degrees, we can get now the location of the voltage maximum. So, let us say this is still we keep it phi L plus 2 m pi. So, the length at which the maximum voltage appears, let us call that as L max, that substituting into this will be L max will be equal to phi L plus 2 m pi into the wavelength divided by 4 pi. Substituting for phi L minus 65.3 degrees, that is in radians it is minus 1.14 radians. So, this is equal to minus 1.14 radians. We can get now L max is equal to minus 1.14 plus 2 m pi lambda divided by 4 pi. Now, substituting different values for m, you put m equal to 1, m equal to 2 and so on, you get the L max or the location where the voltage is going to be maximum, that is 0.41 lambda, 0.91 lambda, 1.41 lambda and so on. To find out the current maximum occurs where voltage is minimum. That means when the phase creates destructive interference, either we can go by that argument or we can say that the current maximum and voltage maxima are shifted by a distance of lambda by 4. So, if I add lambda by 4 or 0.25 lambda to all this value, I will get the location of the current maximum. So, by substituting into this, I can get the location for the current maximum. Current maximum occurs at these values plus minus 0.25 lambda, and even if I subtract 0.25 lambda from here, I still get a length positive. So, I have to choose even that value of the distance. So, the location at which the current is maximum, that will be at 0.16 lambda, 0.66 lambda, 1.16 lambda and so on. So, you see, using the basic equation which you have derived for the transmission lines, if we systematically proceed, find the reflection coefficient, go to the relationship of the voltages and currents, write down the simple voltage expression and the current expression on transmission line, and substituting the values of the reflection coefficient, its magnitude, its phase, we can calculate the maximum and minimum currents on transmission line. We can also find the location at which the voltage or currents are maxima or they are minimum. So, this is one of the problems which you will be asked to solve in the real life, because normally a line is terminated in an unknown impedance and we are supposed to find out, right, where the voltage will be maximum, right, and so on and so on. Let us consider another problem. Let us say now we are having a transmission line which is having a characteristic impedance of 50 ohms, and this line is connected to a parallel combination of 100 ohm resistance and a 1 nanofarad capacitance. In fact, this is a very common problem whenever we are having a cable at high frequencies, and let us say I want to connect this cable to some circuit whose output impedance is about 100 ohms. It is possible at that point we may have some stray capacitances, or intrinsically the impedance might be having a capacitance. So, invariably you will see the output or input impedance of a circuit which will be a combination something like this. So, here the impedance in which the line is terminated is 100 ohms in parallel with 1 nanofarad capacitance. We are supposed to find out what is the VSWR on the line at a frequency of 2 megahertz. Also find the maximum and minimum resistance seen on the line. So, two things we have to find out. First thing, we have to find out what is the VSWR, because that is the measure of how much power is reflected on the line, and also we are interested in finding out what is the maximum and minimum resistance we will see on the line. Again we proceed the same way. So, the problem we are having is a line which is connected to a resistance of 100 ohms and a capacitance of 1 nanofarad. So, this is 1 nanofarad, this is 100 ohms. The characteristic impedance of the line Z0 is given as 50 ohms. So, we have to find out the quantities VSWR rho and R max and R min. Again, the first step in this calculation, first thing we have to now do is find out the complex impedance for this combination of the resistance and capacitance. Once you know the impedance, then you find out what is the reflection coefficient. From the reflection coefficient, you find out the magnitude of the reflection coefficient, and from the magnitude of the reflection coefficient, then you can find out what is the voltage standing wave ratio, VSWR rho. So, the impedance, load impedance Z L is the parallel combination of R and C. So, this is given as R divided by 1 plus j omega R C. The frequency which is given is 2 megahertz. So, the omega at that frequency is 2 pi into 2 into 10 to the power 6 radians per second. So, omega will be 1.256 into 10 to the power 7 radians per second. Substituting for omega and RC, R is 100 ohms and C is 1 nanofarad, we can get 100 divided by 1 plus j 1.2566. So, omega RC, by substituting the value of omega and R and C, you get this quantity 1.2566. So, that impedance will be 100 divided by 1.6 with an angle 51.5 degrees. So, the load impedance I can write either in the polar form, which is 62.3 angle minus 51.5 degrees, or in the real and imaginary part, which is 23.9 minus j 45.6 ohms. Once I know the load impedance now, I can find out the reflection coefficient. Gamma L, which is ZL minus Z0 divided by ZL plus Z0. So, that is equal to 23.9 minus j 45.6 minus 50 divided by 23.9 minus j 45.6 plus 50. By solving this, we get the reflection coefficient as 0.6 angle minus 88.3 degrees. So, the magnitude of the reflection coefficient from here we can get, and that is equal to 0.6. So, we get now from here the magnitude of the reflection coefficient mod gamma L, that is equal to 0.6. Once we get that, then the VSWR rho is 1 plus mod gamma L divided by 1 minus mod gamma L, that is equal to 1 plus 0.6 divided by 1 minus 0.6, that is equal to 4. So, for this combination of resistance and capacitance at 2 megahertz, we will get a VSWR of 4. Once we know the VSWR, then finding out the maximum and minimum resistance is very straightforward. We know the characteristic impedance of the line. So, the maximum impedance will be characteristic impedance multiplied by rho, and the minimum impedance will be characteristic impedance divided by rho. So, we get R max on the line, which is Z0 into rho, which is 50 into 4, so 200 ohms. And R min, minimum resistance, which we will see on the line, is Z0 divided by rho, that is equal to 50 divided by 4, that is 12.5 ohms. So, in this case, we were given some combination of lumped circuit with which the line is terminated, and we were asked to find out what is the maximum and minimum resistance C on the line, and also we were asked to find out what is the VSWR, which we will see on the line. And recall, higher the value of VSWR, worse is the match. So, this VSWR is quite large, it is 4. That means, in this case, a lot of power will be reflected from this terminating load. Let us now try to solve some of the problems by using the Smith chart, that is the graphical means of solving the problem. Before we get into specific problems, let us first try to identify some of the special points on the Smith chart. So, let us say I have to identify some of the special points, that is, I am given the impedance 50 plus j 75 ohms, you have to mark this on the Smith chart, or the impedance 10 plus j 0 ohms, or an impedance 0 minus j 80 ohms, or a reflection coefficient, that is 0.3 angle 60 degrees, or you have to mark a constant VSWR circle with rho equal to 2.5, or we have to find out the R min point on a VSWR circle which is having value 1.5. As we know, all the impedances which we see on the Smith chart are normalized impedances. So, the first step towards marking all these points, impedance points on the Smith chart, is to normalize these impedances. So, firstly, we take the characteristic impedance of the line, let us say it is 50 ohms. So, we have to normalize these values with 50 ohms. So, if I normalize this impedance A, which is 50 plus j 75, this will become 1 plus j 75 upon 50, so that will be 1.5. Now, I go to the Smith chart, and first I identify a circle for which the resistive part is 1. We know this is the circle which passes through the center of the Smith chart. So, this circle is R equal to 1 circle. Then I go to the reactive part, which is 1.5. So, this circle, which is a 1.5 circle. So, the intersection point of these two circles, this circle and this circle, is the point A here, which represents an impedance 50 plus j 75 ohms, or in normalized term 1 plus j 1.5. If I take impedance 10 plus j 0, again we normalize this impedance with 50 ohms. So, this will be 0.2 plus j 0. So, immediately we notice that this is the resistive impedance we are talking about, and the resistive impedance must lie on the horizontal axis in the complex gamma plane. So, we go to a a circle which is r equal to 0.2 circle and find its intersection on the horizontal axis. So, this point B represents an impedance which is 0.2 plus J0 in normalized terms, or 10 ohms plus J0 in the absolute terms. The third impedance which we want to mark on the Smith chart is 0 minus J80 ohms. Again, we normalize this. It is a purely reactive impedance, and since there is a minus sign here, it is purely capacitive reactance. Its normalized value will be 80 divided by 50, so 1.6. Since it is a capacitive reactance, we know it must lie on the lower half of the Smith chart. Smith chart is impedance. The lower half of the Smith chart represent the capacitive reactances, impedances, and the upper half represent the inductive impedances. Since the real part is 0, we know that this point must lie on the outermost circle on the Smith chart. So, if I go to the outermost circle, which is this circle on the Smith chart, and find the constant reactance circle which is having value minus 1.6, I will get this point C. So, this point C represents a pure reactance of minus J80 ohms, or in normalized term minus J 1.6. Now, these were the marking of the impedance points on the Smith chart. Suppose somebody gives me the reflection coefficient, its magnitude and its phase, and asks me to mark that point on the Smith chart. Let us say the magnitude of the reflection coefficient is 0.3 and the phase of the reflection coefficient is 60 degrees. What do? First, we measure the length of the Smith chart here, and that length is 1, because we know the Smith chart in the complex gamma plane has a radius equal to 1. So, this length now is from center to this point is unity. Now, we can scale it to find out what should be the length for 0.3, and then the angle is 60 degrees, which is measured from the real axis in the gamma plane, so which is this line. So, from here we read the angle like normal convention, that go in the anticlockwise direction by 60 degrees, take a radius vector whose length will be 0.3 normalized to this length, and you will get this point D. So, the point D represents a reflection coefficient whose magnitude is 0.3 and whose phase angle is 60 degrees. The another thing which you would like to get is draw a VSWR circle for rho equal to 2.5. How do we draw this circle? We know the rho corresponds to the maximum normalized resistance seen on the transmission line. So, this constant VSWR circle for rho equal to 2.5 must pass through a point which is normalized 2.5 and reactance 0. So, we just find out a circle which is 2.5, r equal to 2.5 and x equal to 0, that means it is this point lies on this line. So, this point represents here normalize r maximum of 2.5. If I draw a circle passing through this point with the center as the center of the Smith chart, this circle then represent a constant VSWR circle for rho equal to 2.5. The next thing we want to find out a r min seen on a constant VSWR circle of 1.5. Again, first we draw the constant VSWR circle, then on that circle you go to a location where r will be minimum, and that will give me the value of r min. So, first, since the rho equal to 1.5 tells me the r max normalize, I find out the point which is r max, this is 1.5. I first draw a circle passing through this point. So, this is the constant VSWR circle for rho equal to 1.5. then we know the leftmost point on this circle represents R min. So, if I read this point here, this value corresponds to the R min. So, the R min value from here, that will be equal to 0.75. So, the normalized value of the minimum resistance seen on the line will be 0.75. If I multiply by 50 ohms, then I will get the minimum impedance on the line. So, this was just a small exercise just to identify some points on the Smith chart. When the impedances are given, when the reflection coefficient is given, when the VSWR is given, and then find out some other values. With this understanding now of the basic Smith chart, now we can go to a specific problem which we want to solve by using Smith chart. Let us say I have a 50 ohm line which is terminated in a load impedance of 25 plus j 35 ohms. With the help of the Smith chart, find reflection coefficient in Cartesian and polar form at the load point, reflection coefficient and impedance at a distance of 0.2 lambda from the load end, and the VSWR on the line. So, we have to find out three quantities now. We are given the absolute load impedance, we are given the characteristic impedance, and we have to find out the reflection coefficient at the load at a distance of 0.2 lambda from the load, and also the VSWR on the line. To do this, first we have to normalize the impedance. So, we can calculate the ZL normalize, that is 25 plus j 35 divided by the characteristic impedance, which is 50. So, that will be 0.5 plus j 0.7. So, the normalized impedance which we have is 0.5 plus j 0.7. We take a Smith chart and mark this point. Of 0.5 plus j 0.7. Since its reactive part is positive, this point must lie on the upper half of the Smith chart. So, first we find out a constant R circle which is 0.5, this value, and then we find out a constant reactance circle which is having a value of plus 0.7. So, this value, this R is 0.5 and this X is 0.7, this circle. So, the intersection point of these two, which is point A, this point now represents a normalized impedance of 0.5 plus j 0.7. I can now read off the value of the reflection coefficient, complex reflection coefficient, by measuring this distance and normalizing that with the radius of the Smith chart. That will give me the magnitude of reflection coefficient. I can measure the phase of this radius vector, and that will give me the phase of the complex reflection coefficient. So, if I do that, I get the quantity of gamma L in the polar form, that will be 0.52 angle 100 degrees. You can see from here, this is almost half of this radius. So, the magnitude of the reflection coefficient is 0.52. This angle is close to 90 degrees. So, its actual value is 100 degrees. So, in polar form, the reflection coefficient is 0.52 angle 100 degrees. I can either convert this into Cartesian form by using calculator, or I can measure the projection of these on the horizontal and vertical axis to find out the reflection coefficient in the Cartesian form. So, this same thing can be obtained as minus 0.09 plus j 0.512. So, this is the reflection coefficient in the polar form, this is the reflection coefficient in the Cartesian form. The next thing we have to do is to find out the reflection coefficient at a distance of 0.2 lambda from the load point. Now, for this, so first thing we do is we draw a constant VSWR circle now passing through this point A. As we move towards the generator on the transmission line, we move on this circle and we want to move by a distance of 0.2 lambda. Since the entire one circumference is equal to lambda by 2, I can find what is the angle correspond to 0.2 lambda. So, from this point if I move by 0.2 lambda, I will reach to this point P and I can find out what is the value of reflection coefficient for this point. So, I just move by an arc which corresponds to 0.2 lambda on this, and then its magnitude of reflection coefficient will remain same because line is lossless. So, this radius is same as this radius. The phase of the reflection coefficient we read in the conventional way. So, from the real axis we measure in the anticlockwise direction up to this radius vector. So, the magnitude of reflection coefficient is still 0.52, but the phase of the reflection coefficient is 316 degrees. So, gamma at L equal to 0.2 lambda will be equal to 0.52 with angle 316 degrees. We are also have to find out what is the impedance now at a distance of 0.2 lambda. This is the location which is at 0.2 lambda from the load. You have moved towards the generator by a distance of 0.2 lambda. So, now if I read off the value of the complex impedance, that means find out a circle which is r equal to constant circle passing through this point and x equal to constant circle passing through this point, I will get the normalized impedance corresponding to this point. So, from here I can get the normalized impedance Z bar, that will be 1.4 minus J 1.37. So, multiplying by 50 ohms, the impedance at that location will be 50 into Z normalized, that is equal to 70 ohms minus J 68.5. So, the impedance at this point is 70 minus J 68.5 ohms, and the VSWR from this, if I go to the rightmost point of this circle, this point, this value tells me the VSWR. So, if you read carefully, you can see this value lies between 3.1 and 3.2. So, its accurate value is 3.17. When we are doing graphical calculations, that kind of error is acceptable. So, if the point is lying somewhere between 3.1 and 3.2, roughly we may say the value is 3.15. The accurate value of this point is 3.17. So, we can read off that value and we will get a VSWR rho that is equal to 3.17. So, in this problem we are given the load impedance, we were asked to find out the reflection coefficient at the load at a distance of 0.2 lambda, the impedance at a distance of 0.2 lambda, and also the VSWR on the line. And see, as we mentioned earlier, that without doing any calculation, rigorous calculation, we could estimate all these values on the transmission line. So, the point which was made that, or the use of Smith chart makes the calculations of transmission line extremely simple, can be seen here. If we had used the analytical expression for the impedance transformation, we have to do the complex calculation. In this case, just by drawing now the constant VSWR circle passing through this point, we can just read off the values for the reflection coefficient, impedance, VSWR and so on. Let us take further problem. Let us say now I have a line which is terminated in a normalized admittance of 0.2 minus j 0.5. See, up till now we have used the Smith chart like the impedance Smith chart. Let us now consider a problem where we are dealing with the admittances. Find the location of the voltage maximum from the load end. Also find the reflection coefficient, normalize admittance and normalize impedance at a distance of 0.12 lambda from the load. So, in this case we are given the admittance which is directly a normalized admittance. So, firstly what we are given is y bar which is 0.18. Let us take the Smith chart. At the moment use the Smith chart as the admittance Smith chart. So, now the Smith chart is the admittance one. You take the point which is 0.2 minus 0.5. So, find out a circle which is 0.2 constant G circle, find out a circle which is constant B circle which is minus 0.5. The intersection point of 2 gives you this point here which is YL bar, so normalized admittance at the load point. Now, we are asked to find out the location of the voltage maximum from the load and also find the reflection coefficient, normalized admittance and normalized impedance at a distance of 1.2 lambda from the load. So, first thing, to find out the voltage maximum, since we are using now the admittance chart, the voltage maximum does not lie on this point, because if you recall, the y or the complex gamma axis has been rotated by 180 degrees. So, this point now represents the voltage maximum and this point represents the voltage minimum. So, if I move now towards the generator by a distance till I reach to this point, that is the length at which I will get the voltage maximum. So, first thing, from this normalized admittance I draw a constant VSWR circle, move on this circle by a distance till I reach to this point where the voltage is maximum. So, this distance from here to here, that gives you the distance of the voltage maximum from the load point. The next thing we are asked to find out is the reflection coefficient and the normalized admittance at a distance of 0.12 lambda. So, I move on this constant VSWR circle by a distance of 0.12 lambda in the clockwise direction, because we are moving towards generator. So, we reach to this point which is y bar. If I read off the value here, I get the value of normalized admittance at a distance of 1.2 lambda from the load point. So, I find out the constant conductance circle passing through this, the constant susceptance circle passing through this, and I get the value which is normalized value which is 0.18 plus j 0.28. So, the admittance at a distance of 0.12 lambda from the load is 0.18 plus j 0.28. To get the reflection coefficient, either I can calculate from admittance itself, but we are also have to find out the normalized impedance at this distance. We know from the transmission line property that the normalized impedance inverts itself at a distance of lambda by 4. But if it invert the normalized impedance, that will become normalized admittance and vice versa. That means if I take a point on the constant VSWR circle and rotate on this circle or move on this circle by lambda by 4, I will get a value which will be inverted value of y bar, which is nothing but z bar. So take a diagonally opposite point on the constant VSWR circle gives me the value of z bar, and in this point now the Smith chart becomes the impedance Smith chart. So see, interesting thing, we started on the Smith chart as the admittance Smith chart, marked this point which was the load admittance, drew a constant VSWR circle, moved on this to find out the admittance at a distance of 0.12 lambda, and just taking now a diagonally opposite point on this, I get the quantity which is normalized impedance, and beyond this point I can start treating the Smith chart like an impedance Smith chart. So if I read the value for the normalized impedance at this point, that value will be 1.6 minus j 2.6. So a constant R circle which is passing through this is 1.6, the constant reactance circle which is passing through this is minus 2.6. So this point here is 1.6 minus j 2.6. Once I get that, then the reflection coefficient, now since this is the impedance Smith chart, the real gamma axis is on the right side, I can measure now the magnitude and phase of the reflection coefficient. So the radius of this circle gives me the reflection coefficient magnitude, the phase measured from the real axis in a conventional way up to this radius vector gives me the phase of the reflection coefficient at a distance of 0.12 lambda. So if I take that, from here I will get the reflection coefficient which is 0.7 magnitude, and the angle will be 328 degrees. So this angle is 328 degrees, and this length normalized to the radius of the Smith chart, that gives you the magnitude of the reflection coefficient, and that is 0.7. So this problem clearly demonstrates the effectiveness of the Smith chart for switching over from the admittances to impedances and vice versa. So even if some quantities are given as impedance or admittance, as the need be, you may switch from the impedance to admittance just by taking a diagonally opposite point on a constant VSWR circle and treat the Smith chart as the other Smith chart. So in this case we started with the admittance, took a diagonally opposite point here, and the Smith chart becomes impedance Smith chart. At some other point, if you want to go back to the admittance, again wherever we are, we take a diagonally opposite point, you will get the normalized admittance, and there onwards I can start using the Smith chart as the admittance Smith chart. Just to ask a question, at the load point what will be the normalized impedance? We know the normalized admittance which is given by this point, so this value we know. If you have to find out now the normalized impedance, just simply find out what is the diagonally opposite point on this. So if I just extend this radius vector, I will get a point somewhere here, and if I read off that value, I will get the normalized impedance at the load point. So we can find now the use of the Smith chart for one more thing, and that is whatever number we are having here, it inverts itself to get this number. So we have here admittance become impedance and the impedance become admittance, but essentially what it is doing, it is inverting a complex number. That's what it is doing. So the Smith chart can be used to inverting any complex number. You take the complex number which you want to invert, treat it like a normalized admittance or impedance, mark that point, draw a circle passing through that, take a diagonally opposite point, and you will get the inverse of the complex number. Now we will solve some more problems by using Smith chart, like finding out the unknown impedance, doing the matching problems by quarter wave transformer and the single stub matching. So in the next lecture we will take the impedance measurement problem and also the impedance matching problem by using the Smith chart.